All right, class outside. This is the third section of LaPlace in my book. I think it's chapter 6, whatever it is in your book. Third section, and we're going to be doing second order. So what I did was I've prepared the stuff from the table we need for my example today. I'm just going to have this off screen and on screen when I need it. So that piece of paper is going to go away. A couple of things to deal with before we do anything too tough. There's a book example where they say, what if you wanted on and then off? Because if you remember, the Heaviside function is off and then on. Well, if you wanted on and then off, it's just 1 minus the Heaviside function. Because think about it, 1 minus 0 is 1, and then 1 minus 1 is 0. So you can turn around the Heaviside function with that little trick, just FYI. The book does some examples. They do a resonance without a discontinuity, just to show you that Laplace transforms can handle the resonance case. But here's my thinking on that, and this is good news to you. I would never ask you to do a problem that can be done much easier by Laplace transforms, because you can handle the resonance case. We've already had a test on it. So don't worry about that example. But they do a non-resonance case with a discontinuity, and that's what I'm going to do. I'm going to do one of the homework problems that's an even, so the answer's not in the back. And then just wanted to talk about something for just a second. You might have thought of this. I don't know if you thought of this. Couldn't you just solve the differential equation without the Heaviside function for when t is less than a? Because the Heaviside function is 0 then. And then solve a different differential equation where the Heaviside function is 1. Just put in 1 for when t is bigger than a. So solve two different things. And there's one problem with that, and that is the initial conditions. The initial conditions only apply when t is 0. And that means that on the second try, if you go beyond t equals 4 or t equals 7, whatever the Heaviside function is, if you go beyond it, you won't have any initial conditions. So you won't be able to go anywhere. All right, so let's take a look at my example that's going to rule the rest of our time here. So it's y double prime plus 3y equals Heaviside function with t equals 4, or little a equals 4, cosine of 5, and then quantity t minus 4. That looks complicated, but if you go to the table, this is exactly what we want. We have a Heaviside function times a function of t minus a. So these two little guys have to match. And look, I've got a minus 4, and I've got a 4. So the table applies. That means that I can hit this with the Laplace transform because I know the Laplace transform of this animal. It's that. So if you look at it, I've got the Laplace transform of y double prime, which the book does out for you. It's in the book. So Laplace transform of y double prime is s squared L of y minus s times y of 0 minus y prime of 0. So we have, on my problem here, hang on, we have initial conditions. So y of 0 is 0, that's why that's a 0. Y prime of 0 is negative 2, that's why I have minus negative 2. And then I have plus 3 L of y, that's this thing. Now this equal sign is that equal sign. And here's the Laplace transform of this animal according to the table. So if you notice, this is just the Laplace transform of cosine. Let's take a look. The Laplace transform of just cosine is s over s squared plus omega squared. That fancy looking w is an omega. It's not a w. All right, so my little y in this example is cosine of 5t. Because notice you have cosine of 5t minus 4 in the right parking spot for that Heaviside function to turn into this thing. So this is the Laplace transform version. Now you know what to do. Get the L of y by itself. So I gather the L of y sections, get them together. I get s squared plus 3. You're going to notice s squared plus 3, y double prime plus 3y. That always happens. You always echo back to the differential equation, a lot like the characteristic equation when we did problems that way. All right. Then on this side, this plus 2 becomes minus 2 because I got to subtract it. And this guy is still unchanged. Now, I can solve for L of y just by dividing by s squared plus 3. So I get a negative 2 divided by s squared plus 3. You see the paper just rubbed off a little bit of the marker. And then I've got the e to the negative 4s times s over s squared plus 25. And that's not a plus, that's a times. because I divided by s squared plus 3. So this guy got divided by s squared plus 3. So I'd like to work on that piece right there, because if I can break that up, instead of having two factors down there, if I can break it up according to partial fractions, I save myself a lot of work. And I have the partial fractions right here. So here's the partial fractions for that one piece. So I've got s over s squared plus 25, s squared plus 3. And since this is degree 2, my numerator has to be as plus b and cs plus d. Woo! Heavy duty. So multiplying through by the denominator, s squared plus 25 cancels, so I have as plus b times s squared plus 3. The s squared plus 3 cancels, so I have cs plus d times s squared plus 25. Distributing out and combining like terms, we notice that we have to have a plus c equals 0 because there's no s cubed terms. I have to have b plus d equals 0 because there's no s squared terms. Then I have to have 3a plus 25c equals 1 because there is one s. And then I have to have 3b plus 25d equals 0 because there's no constant term. So this immediately gives me negative a equals c, negative b equals d. I substitute back into these, get them one equation, one unknown, and I get the lovely a equals negative 1 over 22 and c equals 1 over 22. But at least b and d are both 0. Now if you look up here, well, the pieces with s survive, but the constant terms are both 0 in this example. So if you look, turn that a into a negative 1 over 22, that c into a 1 over 22, and that's this stuff over here. So I've got those pieces substituted in, and back to work. We've got the opportunity now to do the inverse Laplace transform. So there's only one case where I have to do a little bit of an adjustment. And that's here, because this guy, according to my table of values, I need to have that square root of 3 in the numerator. I got to have it, because if you look at the table, we're going to be doing sine for this guy, because I don't have an s up here. So I'm doing sine. That means I need an omega. And omega squared is 3. Omega squared is 3, so omega is square root of 3. So I need a square root of 3. I can balance that off with the 1 over square root of 3, and the 1 over square root of 3 is going to live. Now we get the tricky part. Let's try doing the table for those other two pieces. Those pieces that we got from the partial fractions. So I'm hitting that s over s squared plus 25 and that s over s squared plus 3 with the inverse Laplace transform, which can be done. They're both cosines, because cosine omega t handles s, no omega up here, but I have to have s squared plus omega squared down there. Well, I've got omega equals 5 here and omega equals square root of 3 here. So I get a cosine of 5, but it's not just t, it's t minus 4 because of that heaviside function. You know, this guy has to convert back to a heaviside function. This guy, e to the negative 4s, has to convert back to a heaviside function. So you have this funny little shift according to the table. We're doing this line. I'm doing this line. I'm doing the inverse Laplace transform of this. So I'm going to get this not in the bracket. It'll be free of the bracket because I'm using the inverse Laplace transform. So understand, this guy matches cosine. This guy, heaviside function. Don't lose it. So here's the final answer. Check it out. Final answer, y equals this guy, this negative 2 over square root of 3 sine square root of 3t minus 1 over 22 u sub 4 of t times cosine of 5 quantity t minus 4. You should know where all these pieces come from. I'm just following the table. Same thing over here. 1 over 22 u sub 4 of t cosine square root of 3 of t minus 4. This answer checks. I did it. I could pump it out to you if you ever wanted to see it. It takes a good 5 minutes to do the check. I would recommend, because you can easily check for t less than 4, because then all these u's are 0. And it's like solving just regular y double prime plus 3y equals 0. But then, and you can use your initial conditions, and you will get exactly -2 over square root of 3 sine square root of 3t. That's what you'll get for that easy case. Then you turn all these u's into 1's. And then you take two derivatives and pop them in. And everything works out. So exactly one cosine of this animal works. It's worth doing, you guys. So try some Section 3 homework. Bye-bye.